My name is George Greene or Wren Greene. Either one is fine. The title of my talk is called Geologically Inspired Nanofabrication. And what I'm going to describe is a sort of technology that grew out of some very fundamental work that we did studying a geological phenomenon called pressure solution. So again, unless you're a geologist, odds are you've never heard of pressure solution, but what it is essentially a fundamental process of chemical compaction that occurs in sedimentary rock. And pressure solution presents itself in the rock as these highly flattened intergranular contacts. So the reason that these form is that where these two grains were in contact, the solubility of one or both of those materials at that intergranular contact is enhanced relative to the non-contact region, so you get essentially a mass transport phenomenon leading to the flattening of the grain. Now, the geologists have always attributed this effect as being essentially a phenomenon of mechanical pressure, essentially mechanically stressing the bonds, changing the chemical potentials. But this explanation ignores the most curious aspect of pressure solution, which is that it is almost predominantly observed between the contact of dissimilar materials, right? So the classic example is mica and quartz. Again, up here you can see these are mica grains, these grains here are quartz, and wherever the mica is in contact with quartz, you get pressure solution and flattening. Now compare that to, just a few microns away where quartz is in contact with quartz, you don't have any of this flattening, indicating no pressure solution there. So we set out in our early experiments to try to understand what it is about these asymmetric interfaces that can have an impact on dissolution rates. And these early experiments were run using a technique called a surface forces apparatus. Essentially what you do is you have two surfaces with these semi-reflective mirrors. This creates a interferometer, and we use essentially a type of white light interferometry which allows us to monitor in real time the dissolution of this quartz with a resolution of around an angstrom, so essentially on the atomic scale. Now, a breakthrough came when on a whim, so first of all, what happens if you take a piece of mica and you press it up against quartz? Well, believe it or not, as soon as you press the mica down against the quartz starts to dissolve, and essentially the dissolution rate will sort of decay, and then you get these spontaneous reactivation events. And so long as you maintain pressure, it will just continue to dissolve fast and slow, essentially forever. Now, a breakthrough came when we decided to wire up these silver layers, and we ran that through a voltmeter. And when you bring the mica and quartz together, you measure a voltage. So this voltage is essentially the difference in the surface potentials of the mica and the quartz. And what we saw was quite curious, which is that as the dissolution rate of the quartz changed, the measured voltage that we observed changed. And when we plotted the rate of dissolution as a function of the measured voltage, we got this exponential curve. And I'd like to draw your attention right here to this number, which is essentially 24. Now this is the value of kT over E at room temperature. So this was our first hint that what we were looking at was actually an electrochemical phenomenon. And in fact, through subsequent studies, it turns out that pressure solution is very similar to electrochemical corrosion, which again is odd because there's no oxidation or reduction reactions happening in the dissolution of silica. So more recently, we discovered a very curious phenomenon related to pressure solution, and it came about in this experiment here. And what we were trying to do is seeing if we could essentially do pressure solution in the AFM. And the experiment that we ran was quite basic. Here we just took a diamond-coated AFM tip, pressed it down against a silica surface, and then we just basically waited a few minutes and came back and imaged the surface. And typically what we would observe are little tiny dissolution pits around 5 or 10 nanometers deep. Now in this experiment here, we had the gain on the AFM set a little bit too high, and it drifted into a feedback loop, and the piezo started to ring audibly. Because of the way that the AFM setup is, once you start a measurement, you can't abort. So we had to sit there with this deafening ring in the lab, and when we came back and did the reimage, what we saw was quite remarkable, because instead of these little tiny holes, we got these massive dissolution pits. Now, we're not showing it here, but basically this pit here is nearly 1 micron deep, right? So we obviously set out to try to run a more controllable experiment. So we tried to replicate this result using a process known as force modulation mode. And so what we do is we run the same experiment. This time what we do is we press the AFM tip down onto the surface, and over top of that set point force, we apply a sinusoidally oscillating pressure, right? So if you keep the set point force and the oscillation amplitude the same, and you vary the frequency, what we saw is actually, quite surprising to us, because if you look here, when you oscillate the frequency at 3 kilohertz, you get these tiny dissolution pits. Then at 6 kilohertz, they get a little bigger. And at 9 kilohertz, they get massively big. And then as you increase the frequency again, increase the frequency again, they start to get smaller. Now, when you plot essentially the whole volume as a function of the frequency, you can see that the frequency dependence is very, very sharp. So this indicates to us that what we're looking at is a type of resonance phenomenon. And more importantly, if you look here at the peak dissolution, right? So this dissolution rate right here is a dissolution rate enhancement of the silica surface of 10 to the 7, so 10 million times faster than silica should normally dissolve. Now, these are the kind of etching rates that you get in solutions of hydrofluoric acid, but we're observing them in essentially deionized water. All right. So what I'm going to do is sort of give you an abridged version of the pressure solution mechanism. And so to understand it, the first thing we need to consider is what happens if you take a silica surface and you put it into water. Well, the first thing that happens is the surface becomes hydrolyzed, and that process produces a mixture of different functional groups. So you've got anionic groups and cationic groups and neutral species, and they're all being created at that silica surface. Now, for the silica surface to dissolve, you've got to remove these groups from the surface, but the charging of that interface basically produces an electric field. This electric field, which is captured by a value we call the Stern potential, or the electric field at the solid-liquid interface. And this electric field has an impact on the charge transport properties of these ionic species, specifically the anion and the cation groups. Now, because silica charges negatively, the electric field generated by that silica surface will actually enhance the rate of dissolution or the removal of the anionic charge, and it will suppress the removal of the cationic charge. And so the equilibrium Stern potential that you observe is actually the point at which those two processes are in stoichiometric equilibrium. All right. Now, what happens when you bring a second surface into close proximity to the silica surface? Well, if these two surfaces have different charges, the electric field from one surface can start to influence the electrical environment of the other surface, particularly once you get below the Debye screening length, and these surfaces are only, say, nanometers apart. Now, in the case of silica, what happens is you get a shift in the Stern potential by that confining surface, and that shift in Stern potential will actually shift the system into a new equilibrium. That new equilibrium obviously has a higher rate, and this is the pressure solution effect. Now, what happens when you oscillate the pressure? Well, when you oscillate the pressure, what you're doing is you're actually subtly changing the separation between those surfaces. And this has the impact of oscillating that Stern potential field. And you shift the system out of equilibrium, and you're changing the Stern potential faster than the system can re-equilibrate. And when you hit this essentially dynamics that are essentially coherent with the dynamics of the chemical reactions, you can get these resonant phenomenon and even further enhancement of the dissolution rate. So this is what we call the frequency-enhanced electrochemical pressure solution. So what we've been able to do is to harness this frequency-enhanced electrochemical pressure solution to do a type of direct write lithography in the AFM. And the way that you do it is you simply use an off-resonance tapping mode, and you tune the tapping frequency to the resonant frequency of the pressure solution, right? So it's usually somewhere around 5 to 10 kilohertz, right? So essentially in the audible frequency regime. And once you've tuned the cantilever, as you scan it across the surface, you etch the silica underneath that tip. And because you're making intermittent contact with the surface, there's very little tip wear or damage. And over here, this, is experiment showing the different etching depths that we achieve simply by changing the speed at which we scan the probe. This is the relationship between the trench depth and the tip velocity. And again, we see it follows this power law relationship. So using pressure solution, we've been able to make these nanochannel arrays that are all uniformly etched at around 4 nanometers. Over here is the world's smallest Australian flag, right? So the technology we have here is sort of analogous to a technology called the nanofraser or a thermal probe AFM. So the main difference here is that the nanofraser sort of etches a photoresist material, and then you have to transfer that pattern into an inorganic substrate. So here we can basically etch inorganic substrates directly using this effect. And so the experiments we're showing here were all done in silica, but we've been able to do pressure solution in a wide variety of substrates, including sapphire, gallium nitride, gallium arsenide, silicon wafer, so forth. Now, just like the nanofraser, we wanted to see if the feasibility of doing sort of grayscale lithography. Now, what we've done is relatively crude, but simply by varying the velocity that we scan the tip, we're able to basically get these smooth transitions in the depth at which we etch. So here we basically increase the scan rate and then decrease the scan rate. And you can see here from our profile that initially we've got very deep, then it gets shallow, and then it gets deep again. So we believe if we use this effect and we use sort of more sophisticated control, we should be able to achieve the same type of grayscale lithography that people can do with the nanofraser. All right. Sorry. So finally, in addition, because the pressure solution effect is highly localized, we can basically use it to do nano-imprint lithography. Here, very simply, we just take a pattern surface, press it up against silica in water, and we're able to basically etch that pattern underneath. Now, this was done using the nanolithography equipment at the MCN. And we're currently working out ways that we can get frequency enhancement here, all right, so that we can speed it up. All right, questions? Thank you very much.
Any questions at all? I have many, but beautiful stuff. I really enjoy. But this dissolution effect, suppose it relies on overlapping the double layers of the two material. Yeah. What happens if you try to cancel off one of the two, like you bite your tip to a part?
Yeah, sure.
Zero.
So pressure solution can enhance the solubility, but you can also suppress it, right? And I didn't show it here, but we basically have experiments where we trigger precipitation by using that suppressed. So you locally suppress the solubility, yeah. But the talk's too short, right?
Carry on afterwards. Thanks
Good.
again.